Okay, we'll pick this up from where we left it last time. For most motion that we deal with in our everyday experiences, these are the forces we deal with. There is what we call the normal force, the contact force between any two objects. Whenever two forces touch, there is a normal force between them. And the word normal means perpendicular. It is normal to the surface, perpendicular to the surface. Now, the other force that we deal with in our everyday experiences is what we call the weight, or sometimes the gravitational force. The gravitational force is proportional to the mass of the object and the gravitational field at that point. Notice the way I call it gravitational field, not just acceleration, because a standing still object is going to still feel the gravitational pull of the Earth. Now, let me try to repeat that. If I have a table, I place an object on it, that object still has a weight, even though it's not moving. So that small g cannot be referring to just acceleration due to gravity. It is really a measure of how strong the gravitational effects at that point, and the term that we use for it is gravitational field. Now, friction, whenever two objects, the two surfaces are against each other, they are going to experience friction. And it's a little bit trickier than what most of us think. We'll talk more about it in detail in a little bit. And then the tension is whatever force is exerted through a string. Like when you pull something with a rope or a string, the tension in that string or cord or whatever you want to call it is what we call tension. The force along that rope is what we call the tension. Okay, one good place to play with forces along one direction is the simulation called Forces in 1D that's available at the website phet.colorado.edu, phet.colorado.edu. One nice thing is they allow you actually to download the actual simulation and run it on your own computer. Okay, that's what I'm going to do right now. I'm going to run the version I have downloaded. I'm not going to go to their website. This is the version I have downloaded. Okay, it looks like this. So what we have here, we have our familiar tree and house. We have options here on top. It seems it's mainly, I honestly didn't look at it for a while, but we can change the background color if you don't like this color. Okay, now you can type in values for the applied force here if you want, or you are going to be able to do it by just let's see here, or you are going to do it by just pushing against the cabinet. You can actually change the cabinet to other objects: textbook, fridge, dog, crate, whatever. Now we have another thing that's available here, a diagram. So actually I can pull it. Oh, oops. Come on here. Okay. So I had to click on it. I forgot that I had to do that. But you click on this icon here, and then it makes it in a pop-up window. And actually through here, you can decide the value of the forces. Now you notice here, when I don't have any force to apply, let me clear it again so it resets. When we don't apply any force on the cabinet, we still have two forces present. The gravitational force pointing in the downward direction and the normal force pointing in the upward direction. The normal force is acting on the cabinet due to its contact with the floor here. So it is the floor exerting a force on the cabinet. And then there is the gravitational force, that is the Earth pulling down on the cabinet. So that's a force exerted by the Earth as a whole pulling down on the cabinet. Actually, you can do a lot more things here. You can remove the friction if you want. You can tell it not to show particular forces or show them. You can decide on the barriers. You can decide on the initial position of your cabinet. Now, initially it looked like this, but I invoked more controls by clicking on this button. So you can change the gravitational pull to check, for example, what would happen on the moon. Notice here how the forces get smaller. What would happen if we are in outer space where there is no gravity at all? So there is no forces. It's kind of a little curious that the house and the tree remain looking the same, and we still have the paper looking like that. But nevertheless, if we have no gravity, we have no forces. And what would happen in Jupiter, where the gravitational pull is much stronger than here? Then you can also change the mass of the object. In this case, we have it at 200 kilograms, but you can set it at any value you want. Okay. And you can change, we'll talk later on about these. We have two types of what we call coefficient of friction. One is a coefficient of static friction, and it is set at 0.3 here, and one coefficient of kinetic friction, and it is set at 0.2 here. We'll talk about those in a little bit. I'm going to restore defaults. Okay, now we can actually graph the applied force, the acceleration, the velocity, and the position. And you can graph them all or one of them at a time. I'm not going to graph anything at the beginning. I'm going to focus on this diagram. Let's put it here. And we are going to go back to the simulation and spend probably a whole recording just discussing different cases here using the simulation, because it will help us see things conceptually, I hope. Okay, so I'm going to push. Okay, but even though I'm pushing, okay, the force I'm applying, I'm not going to be able to point to it, but if you look at the diagram that shows the forces on top, it has the yellow force, that's the normal force, the gravitational force, that's the purplish force, and then a blue tiny force, that's my applied force that you see also here, and the friction force. Notice here, all the forces that are applied are balanced, and we don't have any motion, any acceleration of the object. The yellow and the purple are balanced, are along the vertical and balanced, and the applied force Fa and the friction force must be balanced as well, and that's why we don't have acceleration. Now, as I increase my applied force, what's curious here is that the friction force increases as well. Notice that? Okay. It is increasing. We still don't have motion or acceleration. We don't have either. Okay, I need to be careful here whenever I use the words, because we have the tendency to speak of having motion, when actually I should be talking of having acceleration. Because remember when we talked about Newton's first law, we said we can have motion without having an unbalanced, when our forces are balanced. We don't need a force or an unbalanced force to have motion. Okay? If there is no forces acting on an object, if it already has motion, it's going to continue at its state of motion without any forces. Now, in other words, when the forces are balanced, we can have motion or we can have no motion. It does not matter. But when the forces are unbalanced, what's going to happen? We are going to have acceleration. So I need to be careful when I talk. I need to be saying more, we don't have acceleration. Even though I increase my force, then the friction force curiously increases, keeping the forces balanced. And my fridge is not moving. And I keep on increasing. Let me take back. And my fridge is not accelerating. Okay? So you see, even me, I make that mistake. So it's a very difficult concept to word it properly, but it is a very important concept conceptually. Okay? So I increase my applied force, and curiously the friction force increases, and we don't have acceleration. Now I keep on increasing, and look here. What happened is, suddenly my applied force is became larger than the friction force, and we have acceleration, and the object started speeding up. Okay, now I'm going to pause. One nice thing with this kind of simulation, I can rewind and play it back. What I want you to pay attention to, the fact that friction kept increasing until a certain level, and then suddenly it stopped from increasing. Actually, if you pay attention, it suddenly dropped in value. And my fridge started accelerating. Okay, let's look here. So this is again a replay of what I did. Okay, it's taken a little bit more time since I talked. Taking a little bit more time than I want. But anyway, okay, as I increase my applied force, the friction force increases. And I still have balanced forces along the vertical, these two, along the horizontal, these tiny ones. And what's important is that the forces are balanced in every direction. And if they are not balanced along a particular direction, we will have acceleration along that direction. So we keep on increasing Fa, and curiously, the friction force Ff increases at the same level. Okay? It's like the surfaces know, and the more applied force you give, the more friction they give. What's interesting here is to note, when I was applying no force at all, there was no friction. That's a little counterintuitive. You think that if an object is sitting, there must be a friction on it, but no. Friction comes into play only when we start applying the force. It comes into play to counteract our applied force, to balance our applied force. And actually, in this particular case, since we don't have motion, this type of friction, we are going to call it the friction of no motion. And the friction of no motion, the term that we use in physics instead of saying no motion, we call it static friction. Static friction. So that's what we have right now, static friction. A large static friction force that came into play to balance the applied force here. Okay, let's see here the timing. Okay, it's increasing. Pay attention to the friction force. It still keeps on increasing right now. You can pay attention to it here as well. The size, it is equal to Fa. applied force equal to friction force. You notice during the whole procedure, Fg and Fn never change because there is no reason for them to change. One is due to the gravitational pull of the Earth, and the other one is due to the floor pushing on the cabinet. That's another thing to pay attention to. Floor and Earth are two different things. The floor, or if the cabinet was on top of a table, it would be different. Okay, let's see here. I'll go back to that point a little later. But you notice here the friction force is still large, and suddenly it gets smaller. And I have a total force. What's my total force? That's the unbalanced force. So that one, suddenly my unbalanced force came into play when my applied force became larger than the friction force. And notice here at some juncture, I removed the applied force, so my only force remained as the friction force. Okay, but we are not seeing what's happening here, so we will not worry about it for now. Okay, let's go back to the slides.